More complicated problems generally require more complicated solutions. We can model these types of more complicated issues by adding in more equations or constraints to the problem. We call this collection of equations a system. If we model it correctly, a lot of problems can be solved by asking for what values of variables make the equations in the system true. One of the simplest systems we can have is a system of linear equations like we have here. We have two equations, both of them are linear and with two variables, and we can solve this a number of ways. Algebraically, we can use what's called substitution or elimination, which is my preferred way of solving them. We can also use geometry, the graphical representation of these lines, to find the solution as well. For this one, I'm going to solve using substitution. I can take y equal the bottom equation, y equals 3x minus 3, and I can plug this thing right into here, into this y. All this stuff just goes right into there. What this does is it gives me 3x minus 2 times y. Well, y is just 3x minus 3. So 3x minus 3. And then, of course, the equals 5 is still there. This is a linear equation in one variable, and we know how to solve these already. We just solve for x. So I'm going to distribute the negative 2. Plus 6 there equals 5. Combine these two like terms here, that gives me negative 3x. I'm going to subtract the 6 to the other side as well, just to save some space. 5 minus 6 is negative 1, and then divide by negative 3. That gives me x equal to 1/3. Now we know what x is. Let's figure out what y is. We can take this, what we just found, and plug it back into the second equation. That's what y equals. That gives us y equal to 3 times x, which is 1/3, minus 3. So I just plugged x right into here, into this spot right there. And then simplifying, 3 times 1/3 is 1, minus 3 is negative 2. My solution is the coordinate 1/3, negative 2. So here I have the system graphed. I have, you can see on the left hand side there, 3x minus 2y equals 5 and y equals 3x minus 3. This was the system that we had. And you can see here that the red and the blue lines, they cross right here at this point, which if you look on the x-axis, that's going to be 1/3, and the y is negative 2. So the point that we actually found was where the two lines intersect. And where two lines intersect, this is called a conditional system. So 1/3, negative 2, this is the conditional solution. That's what this system is. It's a conditional system. These are typically the ones that are what we want to find, is where we have a single solution. Now, in addition to conditional, there's two more types of solutions. That is inconsistent. Inconsistent. This means no solution. And then the last type is called dependent. This means infinite solutions. Just like in the solutions for linear equations, we had conditional, inconsistent, and identity. This one also has 3 solution types: conditional, meaning one solution; inconsistent, meaning no solutions; and then dependent, meaning infinite solutions. We've got 2 equations, and this one, to me, screams addition or elimination method to solve it. And I can tell that because the columns are all lined up. I have a column of x's, a column of y's, a column of equal signs, and a column of numbers. If they're at all not lined up like that, you can move things around until they are lined up, and then elimination works out very nicely in this part. What you're trying to do is trying to get one of the variables, either x or y, it doesn't matter which, just choose one. One of them to have the same number but opposite signs in each equation. So for me, I'm gonna look at the y's here. So just keep in mind these y's. Let me highlight them here. We have 4y and 2y. What I'm going to do now is I'm going to multiply the equations by something to get the number to be the same in front of the y's, but have opposite signs. And I chose the y's specifically because all I have to do is multiply the bottom equation by -2. If I multiply everything by -2, that will get me what I want. So the top equation stays the same, x plus 4y equals 4. And the bottom equation now becomes -2 times 5 is -10x. -2 times +2 is -4y. And -2 times 16 is 32. And now you see that the y's have the same number in front, the same coefficient, but opposite signs. This is important because what I can do now is I can add the two equations going straight down the columns. So we're going to go down this column of x's. X minus 10x is -9x. 4y minus 4y cancels. And that's the whole reason why we did that whole process in the beginning. It gives us just 0. And 4 plus 32 is 36. So of course, the plus 0 just goes away. And we have -9x equals 36. We just divide it by -9. And we get x equal to -4. Now that I have my x variable, I need to figure out what is my y variable because we're looking for an ordered pair here. And to do that, I'm going to take the given x variable that we just found. I'm going to take this thing and plug it into one of the original equations. So whichever one of these you want to plug it into, the top one or the bottom one, I'm going to choose the top one, the x plus 4y equals 4. And that's because it looks the numbers look smaller to me. So plugging that in, I get x, which is -4, plus 4y equals 4. Now I can solve for y by adding the 4 and dividing by 4, giving us y equal to 2. And there's my other variable. We have x, we have y. That gives us an ordered pair, -4, 2. And that means that this is a conditional system. Here's the graphed representation of the system. We have our functions that are actually graphed. There are linear equations there. And you can see that the point that they cross is -4, 2. So that's the geometric, the graphical representation of the system being solved, and the algebraic version as well. And I used elimination or addition to solve that. Okay, for this system, this is telling me that I should use substitution, and the reason why is because we have x equal to something. When x is equal to something, that's very easy to solve for substitution. You just plug this thing in for whatever x is. Just plug it into there, and we'll be able to solve. You can, of course, solve using substitution or elimination for any equation that you have, or any system, I should say. It's just kind of whatever you're more comfortable with. This one, because it's already solved for x, it's just a natural one to use for substitution. But you can, like I just said, you can just shift things around. Move the 4y to the left-hand side, and then you can use elimination to solve this system just fine. You'll get the same answer either way. Okay, distribute the 2, and we get 8y plus 10 minus 8y equals 10. Combine like terms, we have 8y and 8y. They cancel, and that gives us 10 equal to 10. Now this is a true statement. And what this means is that if you plug in an x variable, you can find a different y variable. You plug in another x variable, and you can get a different y variable. And you will always have you will always find true solutions, no matter what x you choose. You will always find a y that makes it true. And that means that this is a dependent system. In other words, there's infinite solutions. Now, what does that look like graphically? So here are the two lines, and I can graph the first line. It shows up like that. That's my first equation there. And then I will turn that one off and graph the second line. Well, that looks very similar. And in fact, if I graph both of them, let me see if I can choose a different color here. Yeah, that's better. You can see that the two lines are the exact same line. And you can actually see that, but if you were to multiply this top equation, the orange one, by 2, you would get 2 equals 8y plus 10. And if you move the 8y to the left-hand side, you get 2x minus 8y equals 10. It's really the same equation, just changed by a multiple. That's what a dependent system really is. There's infinite ordered pairs that make it true. Okay, this system I'm going to use addition or elimination, and I'm going to cancel out. I'll cancel the x's, I guess. So the top one we have 18, the bottom one we have 6. So I'm going to multiply the bottom equation by -3. That'll give me 18 in the bottom, but -18. So it's the same number, but different signs. That's what you want. So we have 18x, this is the top equation, 15y equals 19. The bottom equation becomes -3 times 6 is -18x. -3 times -5y is positive 15y. And a -3 times positive 2 gives me -6. And adding going straight down, the 18x and the -18x cancel. The -15y and the positive 15y actually cancel. And 19 minus 6 gives us 13. So we get 0 equals to 13. And this should tell you this is a false statement. Therefore, it is an inconsistent system, meaning no solution. So the previous problem, we had infinite solutions because the two lines were the same. The one before that, we had a conditional system. That means that the two lines cross at exactly one point. An inconsistent system is that which never crosses. Or in other words, the two lines are parallel. And here you can see these are the two lines for my system, and they are indeed parallel. You can keep scrolling in either direction that you want to go, and they will never cross, no matter how far you go. So that's what gives us an inconsistent equation, meaning there's no solution. Okay, is 5, -2 a solution to this system here? This curly brace is just showing that this is a system. It's kind of one combined thing. That's all that's being said here. And you can solve this algebraically by just plugging in 5, -2 and seeing what you get. For the first equation, we have 3 times 5 plus 6 times -2 equals 3. 3 times 5 is 15. 2 times -2 is -12. And that does indeed give us 3. So that one's true. Let's check the next one. 5 times 5 minus 2 times -2 equals 28. We get 25 plus 4. And this one gives you 29 equals 28, which is false. So we would say, no, 5, -2 is not a solution to this system. So here's our system graphed. You can see we have our two lines, the red and the black line, and then our point that was asked is 5, -2 the solution. And as you can see, 5, -2 is on the black line. That's why we got a true statement in the first one. But it is not on the red line, so that's why it gives us a false statement. And because 5, -2 is not the intersection where the two lines cross, therefore it is not a solution to this system. All right, for this system, I've got fractions in the top one, and we can utilize the first step in the elimination method to our advantage here whenever we're dealing with fractions, because we can actually get rid of them. Here, I have a common denominator of 2. I'm just going to multiply the top equation by 2. I'm just going to multiply everything by that. All that does is it changes what the numbers are. The relationship, the actual thing that gives us the equation of the line, will not change. It's just going to look a little bit nicer. So 2 times x over 2 is going to be x. 2 times negative y over 2 is negative y. And 2 times negative 1 is negative 2. And now this is much easier to look at. We just kind of ignore this top equation. We can just get rid of it, really. This system is much easier because there's no fractions in it. And we can use substitution or elimination. I'm going to use elimination in this case because the x's, the y's, the equal sign, and the numbers are all lined up. And all I have to do, I can get rid of both of them. I could multiply the bottom equation by -1. That'll cancel the x's. Or I can multiply the bottom equation by just +2. That way the y's will have the same number but different signs. I'm going to do this. That gives me the top equation is x plus 2y equals -11. The bottom equation is 2x minus 2y, and then 2 times -2 is -4. And add these going straight down, we get 3x. Y's cancel. -11 minus 4 is -15. We can just divide by 3. And that gives us x equal to -5, I think. Yep. All right. Plug this one back into the one of the two equations. This bottom equation looks really nice and easy to me, so I'm going to plug -5 into the x spot. Minus y equals -2. That gives me, I can just add the 5 to the other side, equals 3. And then divide by -1, giving me y equal to -3. So my solution is -5, -3, which is a conditional system. It's got a single solution, which is an ordered pair. That means we have a conditional system right here. All right, the last problem we have is a word problem. We have a company that manufactures canoes. There's a fixed cost of $18,000. I'm going to write that down. So this is a one-time kind of fixed cost of $18,000. And it costs $40 to produce a canoe, and each one sells for $80. So $40 is the, so this is a fixed cost. This is the production cost of a canoe, and $80 is the income or the revenue of a canoe. And X is going to represent the number of canoes sold. Okay, so we have to find 3 things here: the cost function, the revenue function, and the break-even point. The cost function is just going to be some combination of the numbers, definitely 18,000 and 40, because both of those are cost. Some combination, some expression of these numbers that gives us the total cost to produce X number of canoes. Well, if there's a fixed cost, that means it's a one-time thing. Think of it like the starting point, or in this case, think of it like a y-intercept. That's always kind of the starting points there. And the cost, the actual production cost of a canoe is 40. That means that it's going to be $40 per canoe. So if you sell 2 canoes, it's going to be 40 times 2. If you sell 18 canoes, it's going to be 40 times 18. If you sell 100, 40 times 100. And if you sell X canoes, it's going to be 40 times X. So we have an initial cost of 18,000, and an additional, so we're going to add on to this, a $40 per canoe. This is our cost function, C of X. All right, so for our revenue function, it's how much money does that bring in from per canoe sold? Well, if we make $80 per canoe sold, and we sell, X canoes, that means we bring in 80X. 80 times however many canoes we sell. Now, we have our cost function, our revenue function, the break-even point. This should make sense what we're kind of looking for here. It's natural to want to find when does your cost and revenue equal each other? When does C of x equal R of x? This is the break-even point. And that is when 18,000 plus 40x equals 80x. Now we can just solve for x. This is just a linear equation with one variable. We had two variables here at the very beginning. This is our system right here, C of x and R of x. And by doing this statement, this is essentially substitution that we're doing here. And that's what gives us this single linear or a linear equation of one variable. That's the whole process we're doing here. Of course, it gives us 40x, and then we just divide by 40. Of course, the zeros cancel. We divide by 2, we get 900. Divided by 2 again, we get 450. So x equals 450. X is the number of canoes sold, so 450 canoes. And the break-even point should be where the cost and the revenue are the same. Therefore, you make no money. You don't lose any money, but you make no money. That's why it's called the break-even point. Let's look at this thing graphed. Okay, here is my system graphed. You can see here that we don't see anything really well here. We see a little bit of a line right here, this purple line, but it doesn't show very well. So what I'm going to need to do is change our labels. If I change the y to be 1,000, you see that we actually see the purple line now quite well. We still don't see the green line, but all we have to do for that is just zoom out a little bit, and we will start seeing the green line. There it is. And we can see the break-even point is right here at this point, and that's at 450 canoes, and that brings in that's $36,000. So that's how much money you spent and how much money you gained from the selling the 450. So of course, anything above 450 canoes, that's going to be all profit. The purple line is the revenue. So the difference between the purple line and the green line, that's going to be profit. How much money you make. And then of course, anything less than 450, this is all going to be a loss. The cost is the green function that is higher than the profit. So you're going to lose money. The difference between those two is how much money you lose. So of course, we want to know, where can we start making profit? That's the benefit of finding the break-even point. Really quick, I want to say one thing about solving by substitution. This system I would solve by elimination because we have x, y's, equal signs, and the numbers all lined up. But if you were to solve by substitution, you need to get one of the equations to have a variable by itself. So I'm going to solve the bottom equation for x. It gives me 3x equals 1 plus 4y. Then divide by 3. And we get x equal to 1 plus 4y over 3. Now I can solve the system by substitution. I just need to plug this thing into the equation, one of the equations. Now, you would not plug this thing into this equation here. You have to plug it into the other equation. That's because we used this equation to solve for the variable. We used this to find this, and you're kind of just doing this whole cyclic thing. It's not what's going to find the solution. You must, so this is wrong. You must plug this instead into the other equation that's there. The reason why you don't plug it into the equation that you already have, I'll show you this here. We had, let's see, 3x minus 4y equal 1, 3x minus 4y equal 1. If we were to plug this thing into this equation that we already found, or we already used, I should say, minus 4y equals 1. 3 times 3, or 3 divided by 3 cancels, we get 1 plus 4y. 1 plus 4y minus 4y equals 1. Clean this up a little bit better. The 4y and the negative 4y cancel, and this gives us 1 equals 1. And this could incorrectly tell you that this is a dependent system So it has infinite solutions, which is a type of solution that you can have, right? But it is not correct in this case. I'm pretty sure in this case you would get an actual conditional system, an actual coordinate pair for the answer. So make sure you always plug whatever thing you find for one of the substitutions. Make sure you plug it into the other equation. Don't plug it back into the same equation.